space mission, which in the past few days has carried the eyes of men farther than they've ever been.
And the science is pushed in amazing.
Just last
like
night,
fitting a jigsaw puzzle together.
had these frames come back miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Good evening and welcome to the 10 o'clock p.m. edition of Voyager Update. I'm your host, Rich Terrell. At 10 p.m. Pacific Daylight Time, the spacecraft is 95,000 kilometers or 58,000 miles and speeding away from the planet at a speed of 55,000 miles per hour. What exactly does it mean to be 95,000 kilometers from the planet Neptune? Well, it means Neptune fills your field of view. It means the spacecraft is now traveling at about 15 miles per second, fast enough to cross the United States in about 2 minutes and 45 seconds. Although the spacecraft has already had its closest approach to Neptune, we will not be receiving data from us. In fact, as we broadcast this update to you, the data from the spacecraft is just passing Uranus and speeding toward us at the speed of light, 186,000 miles per second. The spacecraft right now is behind the planet, not in direct view of the Earth. And during this time, radio waves from the spacecraft are traveling through the atmosphere of Neptune and in hopes of measuring the pressure and temperatures of the atmosphere. We also are about to do a special technique of stellar occultation, where a star is measured as it crosses behind the ring arc of Neptune. We have a brief tape roll that we'll show you now on how the occultation technique works. Okay, and right now we see the star passing behind the rings of Saturn, and you'll see it wink on and off as the star goes behind the thicker parts of the ring. Cassini division, the star comes out from behind the rings and again is occulted by thicker parts of the A ring. This technique was very, very successful in giving us very high-resolution views of the rings of Saturn. It was again used on the rings of Uranus. Here we show the Sun being occulted by the rings of Uranus. Right now we'll be talking and concentrating on rings. That's the theme of this show. We've just had some ring images, the closest ring images we'll ever get from the planet Neptune. And to kind of preface this event, I'd like to read two quotes by two gentlemen, both speaking about the rings of Saturn. One was Galileo, 2 years after he discovered the sea rings. In 1610, using a 25-power telescope, he first saw the rings of Saturn and was puzzled why these two objects on either side of the planet wouldn't move, as he had seen the moons of Jupiter moving. Well, in 1612, the Earth passed through ring plane crossing, so these objects that he saw on either side of Saturn disappeared. And he wrote in a letter, "I do not know what to say in a case so surprising. The shortness of time, the unexpected nature of the event, the weakness of my understanding, and the fear of being mistaken have greatly confounded me." 368 years later, Brad Smith of the Voyager Imaging Science Team, speaking about data taken from, again, another 25-power telescope, the narrow-angle camera on Voyager, said, "We've never been so confused for so long about anything so obvious." Two men speaking about Saturn's rings 400 years apart. One's confounded, one's confused. Well, that's really the nature of science. It's getting yourself to the point of really trying to understand a difficult set of physical observations. We now rest on a great deal of prior knowledge, and our knowledge base is very broad. But to help us understand the level at which we are confused and confounded, we have a guest, Jeff Cuzzy from the Voyager Imaging Science Team and a modern-day ring expert. Jeff, thanks for joining us.
Fun to be here, Rich, especially right now.
Yeah, you're probably as eager as I am to get back to the monitors and look at some of the data. In fact, just as we were introducing this, some rather dramatic ring images came down. But before we show those, let's put the rings of Uranus into a little bit of context. Do you want to describe what we have here? We have a...
Well, you've got a little graphic of Neptune's ring arcs here. Over on the right-hand side, there's a little description of the densest part of the arc, which actually comes in 3 or 4 sort of groups. The entire arc is about 35 or 40 degrees long. And in other images, we've seen that fainter parts of the arc go essentially all the way around. And of course, there is the second arc, the inner arc as well, that goes, as far as we can tell, all the way around. Both of these arcs are bounded on their inner edge by 2 of the newly discovered little satellites, which is somewhat of a unique configuration, as you know. In other ring systems, we tend to see satellites either straddling rings or in the middle of the ring.
Right. So are we certain now that this outer ring is completely closed here? This is one thing we've been fighting with for the last few days to really get closure on this, to make ends meet, so to speak.
Yeah, no, I don't think we actually can say that quite yet. It goes most of the way around, but there's a section that's say 20 or 30 degrees across where it really looks like there may be nothing. It's in the noise, but there may be material that goes all the way around. It's faint enough, though, that the ground-based people that study these rings by stellar occultations probably couldn't have seen stuff anywhere except in the very denser, clumpy regions that all of our retargetables are actually aimed at. And as you know, the ability to retarget these very precious few frames to these ill-defined, ill-described objects in peculiar orbits has really been a coup of the navigation team on this mission, and we're all very grateful to them for their efforts.
That retargeting exercise was one of, there was a bit of drama there. We really got those images at the last minute to allow us to retarget those.
Yeah, that was a squeaker, actually. We got those the 11th that we even saw these arcs for the first time. And as you know, both of us spent a lot of sleepless nights over the last week getting enough data on these things so that the nav team could actually target the orbits. But it all has worked out very, very well, very well.
It was interesting that the satellite people, who were very hungry to see the new satellites, wanted those retargetables very badly and wanted to take them away from us.
Well, the satellites are interesting things, too, and we're interested in the satellites. I guess today we got some very nice images of 1989 N2, and
That's
we'll
right.
get some. I haven't seen the new one of N1, but I'm sure that's going to be a knockout too.
Yeah, fortunately we were able to get everything we wanted. We were able to get the satellites and the ring.
Oh yeah, this has been just great. This has been a success beyond my expectations.
Okay, let's put a graphic. No, in fact, let's just go to the picture, the still store of the latest ring image, and this came down just moments ago, and this is the highest resolution ring images that we'll have. And Jeff, you want to take a first crack? I mean, you're seeing this for the first time,
well,
as are many people.
As you know, Rich, this image makes use, the fact that this image is so unsmeared and so crisp, the resolution in this image is 1.5 kilometers. This is the highest resolution image actually we have of any ring system. And we were only able to do this because the spacecraft was programmed to just take out the motion of the spacecraft going by the ring and keep it from getting blurred. Our other close encounter images we were only able to compensate one of the dimensions of smear. So some of our other high-resolution images are smeared. But this is a beauty, and I've been looking at it. And I think there is some evidence for kind of clumpy kind of distribution along the ring here, which is the kind of thing that we like to look for as a telltale clue, if you like, to the presence of little moons that might be orbiting around in the vicinity of the rings. As you know, that the fates of rings and ring moons in the same region are inextricably interlinked, really. Mm-hmm. So that's, I was also looking at the wide that has now disappeared off the monitors, but the wide is just a spectacular picture.
Well, I think we can have the wide, too. That's the next frame
oh,
that's
there it
come
is.
down.
It is on one over there. It's kind of stretched kind of hard.
Let's see, oops. Let's see if we have the wide. Maybe we can bring the wide up on one while we talk about the narrow angle frame. You talked about this is perhaps the highest resolution image we've ever gotten from any ring system. I find it amazing to think that these ring particles are very dark, aren't they?
Yeah, they are as dark as charcoal briquettes. These things are really dark.
So here we have essentially charcoal briquettes photographed against a jet black background by a spacecraft moving at 15 miles per second with a 1,500 millimeter lens with a camera equivalent to ASA 10.
Right, with a light equivalent to a single Christmas tree bulb at the top of the tree.
That's right. I mean, it's just absolutely extraordinary that we can even do this.
It's quite a feat.
Here's the wide angle
yeah,
frame.
Look at that. That's a great shot. That's both of those ring arcs. The outer one with the main clumpy features. This, as you know, is the trailing part of the ring arc, which we've called Feature C, and We've never seen this kind of structure within it before, but pretty clearly it has some structure within it. And this other one is the inner ring arc at about 53,000 kilometers. Both of these features, things have been seen from the ground in stellar occultations at both of these radii, or close enough that they can be explained by things at both of these radii. But that is just a beautiful, beautiful thing.
Why don't we say a few things about the ground-based stellar occultations? I mean, I think it was amazing that so much was known or hinted at the Neptune rings from the ground, and it actually came true. I mean, just the idea that they're partial ring arcs is kind of a very peculiar statement to make, and one which was founded on very sparse data, wasn't it?
Well, yeah, people actually have said a lot about the ring arc aspect of things. I actually have a graphic here that is kind of interesting. It just points out that other planets have ring arcs as well. This particular graphic shows an arc that was seen in the Encke gap in the outer part of Saturn's rings. Now this is one little gap in Saturn's rings. It's almost lost in the wealth of detail there. But within this gap, there is a little ring arc. That's this little bright feature here. And you can see just by looking at it that it is in fact a little bit clumpy. Here it's bright, and there it's not bright. Also, where we look at this ring arc in different places, we see that it's not continuous. In fact, this graphic here shows that at 2 different longitudes in the rings, you see arcs at different places. At this particular longitude, the arc is in the center of the ring, and at this longitude, the arc is on the edge. And these are not the same arcs, and obviously things just don't go all the way around. So the presence of material orbiting around a planet that doesn't go all the way around is something that we've seen, but we never got as good a look at it as we are going to do at Neptune. So I think to be really able to understand these longitudinally, well, I hate to say confined, because as you know, there are hypotheses whether they're confined or whether they're just transient. But they're certainly restricted in longitude, and that's a major, major puzzle.
Why don't we explore that concept a little bit? We've tried very hard to understand confinement in radius, this whole idea of shepherding moons, where the gravitational wakes of moons on either side of a ring can confine the ring radially. But how do you confine a ring azimutally?
Well, there are various ways that moons can interact. It's all related to the gravity of the moons. And most of these confinement mechanisms are all gravitational. And if you like to think about the way a moon might confine some material longitudinally, in one of the theories that's been proposed for this particular ring involves an inclined moon. And if you think about tilting a moon up on its side and then averaging it down onto the plane of the orbit, you might imagine that all of a sudden now, instead of being a circle with gravity, with the satellite smeared out in a circle, it's smeared out in something that looks more like a football because you've tilted its orbit up. Okay? Now that football effectively defines preferred direction in space. And so it's possible by interacting that gravitational potential, essentially with the ring material, to confine it in space. That's one theory. Another theory has to do with the localization of things at what's called Lagrange points, like the Trojan asteroids. There's a whole little family of asteroids that orbits in the orbit of Jupiter, exactly 60 degrees away from Jupiter.
So moons within the same orbit of the ring material.
Within the same orbit.
That's one of the things we're really looking for in these images.
That's right. We'd love to see a moon at the same radius. That would make this whole thing very easy to understand. But so far we haven't, unfortunately.
Yeah. Now, moons have been seen, though, in the orbits of other rings, like the F ring at Saturn. At least larger particles, clumps that appear to be fairly substantial, maybe several kilometers in diameter.
Well, that's right. In fact, in the Encke gap here, there's been inferred, a moon has been inferred in this gap based on the interactions that you see with the surrounding material. The moon hasn't been seen yet, but it's known to be there. Also, with Saturn's F ring, got another little graphic over here. This is the one that has caused a lot of hyperbole to make its way into the press, too. But we were all really pretty, what was it, confounded and
confused, yes,
this
one.
Right. But these little tweaks and kinks and things like that are now generally understood, I think, to be caused by interactions of the F ring, probably with little moons that we've never seen yet. That just happen to be in the vicinity, and maybe they're on eccentric orbits that brings them close to the ring, and it puts these little kinks in the ring, and so on and so forth. So
we haven't seen them because we weren't looking, or because they're just too small?
Well, they could be very small, and also it's hard to cover. Saturn's ring system is so vast,
Right.
you know, it's even more vast than that of Neptune. It's just hard to cover all those longitudes with these little postage stamp frames that have a good enough resolution to see the little moons that can be doing this. But again, you can infer things based on that, and I think even bright clumps have been seen in the various parts of the F ring itself that might be moons. You can't quite tell, and so on and so forth.
You spoke of the rings perhaps being very young, and one of the reasons you can get around the inability to confine the ring azimuthally is to say, well, it just came to be rather locally in time. How young do they have to be?
Well, you know, this is kind of a concept that a lot of scientists are uncomfortable with, is just saying, well, it's easy to understand this and such because it just happened, or we're just lucky, or something. And people are very reluctant to buy this. But with all the ring systems, we have so many problems with short time scales now, having to do with the brightness of the Saturn ring particles, the torques from the density waves in Saturn's rings, other kinds of dynamical phenomena in Saturn's rings, erosion of the ring material by meteoroids. You know, these things get ground to powder in a time very short on the time scale of the solar system. So we have all these problems that have led people to imagine that one feature or another feature, or maybe entire ring systems, could be transient. In the case of Saturn's rings, for instance, Pioneer 10 and 11 saw things out around the orbit of the F ring that aren't the F ring, and any other satellite in the vicinity that apparently have to be azimuthally incomplete structures, low optical depth. Maybe they're just being caused by objects banging into each other and dumping off whatever's on their surface at the time, and only that stuff gets then swept up by other material in the region, so there's a steady state of getting dirty and getting clean again.
I see. So you don't wind up losing material?
No, the material is generally just passed from the surface of one guy to the other, but it enjoys a brief lifetime as a ring arc in the meantime, and maybe that's what's going on in the Yankee Gap, and maybe that's what's going on in the Neptune's rings, and that's one possibility.
So that gets you out of the predicament of breaking up a satellite and eventually breaking up enough satellites so you've run out of material. So
that's right.
You're just hiding the material temporarily.
You hide the material in the satellites, and because the satellites have more mass in a smaller area than the rings do, you can do that, and then over the age of the solar system, every now and then you'll just bash up another one every now and then, and you have another ring. So this is a sort of a concept that I think a lot of people are starting to find attractive. The dynamical confinement mechanisms may still be correct and true and valid physics and this and that, and I'm sure they are, given that the satellite is massive enough, let's say, or that the ring is close enough to the appropriate resonance, and these are things we won't be able to know until we've looked a lot more closely at this data.
In fact, just today, perhaps one of these confinement culprits was announced. Two new satellites were announced, 1989 N5 and 1989 N6, both orbiting very close to Neptune in orbits around 50,000 kilometers from the center for the, 1989 N5 and about 48,200, I believe, for 1989 N6. N6 is the real maverick. It's all the other moons that were found in near circular orbits in the equatorial plane, but N6 is different, isn't it?
Yeah, it's a cute little moon, I guess.
It's got an inclination of 4.5 degrees.
4.5 degree inclination, and that could be enough for it to be effective in this confinement sort of way if it's massive enough, and that's really the question.
Right. And
it's not very big, as you know.
We've gotten a first clue of the diameters of some of these inner moons. 1989 N3 and N4 were thought to be something like 100 to 150 kilometers in diameter, and very dark. These inner moons are smaller, but still they could be 50 kilometers or more in diameter. Is this really going to be massive enough when theories finally put all this together? Is I guess anyone's guess right at the moment.
Yeah, I think the original theory would like to have a moon that was about 10 times that massive, but these theories have been changed around a little bit. The original shepherding theory has been changed in various ways as we understand the physics better. We understand how smaller moons can maybe do it, and maybe that'll happen in this case too. So it's possible that this big arc really is confined. One question I would have is, well, why then? What's the story with the second arc? Can you? That one doesn't have apparently any obvious region of confinement, any obvious part that's so much more massive than any others. So why? How do you put these two together in the big picture? That's the question that I like to think about a little bit more, because obviously if these same satellites are in the same region, the resonances are, lie pretty much all over that region, and we'd have to address a concept that could explain both of them within the same framework, I'd say.
Do you think the the two ring arcs that are seen are going to be the only ring arcs? Can we explain all of the ground-based occultation data with just those two ring arcs, or do you think there'll be more?
Well, there is, I think, at least one other and maybe two other radii at which things have been seen from the ground at which we have not as yet seen anything. In some of the images we've got in that we're analyzing right now, there are, you know, hints of things that are the radii, and we're actively pursuing that, and that might help. I think some of the, but these observations that at radii which we haven't seen anything yet are unconfirmed. That is, they're single telescope observations. Maybe they're just a fluke or something like that. But I can tell you before we give up, and I'm sure you know, we're going to look very hard at all these radii to really see if we can nail down this. From the standpoint of seeing other arcs, I don't know. That's an interesting question. I'm starting to wonder, you know, as you know, with Uranus, when we passed by Uranus, we had the 9 main rings. We saw them all just fine. We went past, we looked in forward scatter, where you see light that's diffracted and dominated by microscopic particles.
You mean the sun shining essentially through the rings at you?
More or less, right. You're looking back towards the sun, and the light is being scattered towards you, like when you look at dust floating around in a room, you see it better when the sun is on the other side of the dust from you. And in that image, which is a beautiful Voyager image, we saw about 50 or 60 of these bands of material that had never been seen before. So everybody's saying, well, are we going to see this at Neptune too? And I'm not so sure now. The fact that the things that we've seen correspond pretty well with pretty much everything that's been seen from the ground, and we don't really see anything else except for, as I said, this other, you know, material that we might be seeing. I don't know. It's going to be interesting. I think I would have made a more facile prediction a week ago, but I'm not ready to do that anymore.
So you're happy the way things are turning out?
Oh yeah, I think things are just turning out just great. I think that those last pictures, and I think overall the team did a terrific job of you know, covering all of our bets really, and not, you know, because as you remember, we didn't even know when we got there whether these things were going to be in the equator plane. You know, with the crazy orbits of the satellites, things could have been inclined or eccentric or retrograde or almost anything.
Okay. We have an image on Ramtech 3. Is that? Okay, this was the image of Triton that came in earlier today, and that's going to be the focus, I guess, of a lot of what Voyager does later. In the next few hours, actually in the next 45 minutes or so, we'll be getting down a full disk view of Triton. Hopefully try to understand some of these very complex portions that we're seeing. At least to a general view of the thing, it looks very similar to the kinds of features we saw on Europa at Jupiter. And the fact that craters aren't really apparent now with 15 kilometer or so resolution is very intriguing. There's a whole suite of things that are happening now. It's a symphony which is all coming together. And the rings are one part of the story, and the moons are another, and of course the fantastic atmosphere is another again.
I've got this other graphic. Speaking of the symphony, I think this is an interesting thing to
Yes, let's
to point out.
Let's just point out the
various players in these symphonies here.
how the moons and the
Right, this doesn't.
moons and the rings come together.
Right, and this one sort of shows the ring moon systems of all the giant planets plotted on a common scale at distance from the planet, and the scale is not in kilometers or even in the units of the radius of the planet, but what is called the Roche limit. And as you know, the Roche limit is the distance from the planet at which the tides in the planet would be strong enough to disrupt a liquid object. This is just really not a particularly physically meaningful number, but it's a benchmark you can use. You know, just like the moon raises tides on the Earth and you know, causes us to see our water tides, there's also tides in the solid body, and the Earth raises tides on the moon, in the rocks of the moon. And if you imagine moving the moon closer to the Earth, the tides would get stronger and stronger until finally the moon might get torn apart. And the Roche limit is the distance at which a liquid moon would be torn apart by a giant planet. Now, what you see is for all of these giant planets, all of their ring systems, certainly now in the case of Saturn, certainly in the case of Uranus, and Jupiter has a little faint ring, and now we know the various ring arcs and so on of Neptune, all lie inside this Roche limit. Okay, and the other interesting thing you want to know...
So that material inside the Roche limit wouldn't, if it was broken apart, wouldn't necessarily come back together to form a moon.
With increasing difficulty, I think, and in fact this inner limit here is the limit at which two particles of equal size could not hold themselves together by their own gravity. So this really is sort of an inner accretion limit, and I think it's extremely interesting that for all of the giant planet systems, generally speaking, and you got to allow yourself the usual grain of salt with these things, they have an inner boundary very close to the accretion limit and an outer boundary within the Roche limit. The other thing I think is absolutely fascinating about this is the transition between relatively large moons further out in the system and more numerous but smaller moons closer in. Like in the case of Uranus, here's the 10 new moons discovered by Voyager. Neptune, now we have a whole suite. Saturn, we discovered about 6 out here. And in fact, there's even one inside Saturn's rings in the Yankee gaps I mentioned. Jupiter has 2 within the rings back in here. And to me, this is becoming a fascinating picture with a lot of clues as to what's going on here. Why do we see this pattern in all these systems? I think once we finally understand this pattern, we'll understand an awful lot more about the processes by which these giant planets were formed.
And one other thing your graph points out is that the rings, the moons discovered around Neptune are somewhat larger and more massive, and perhaps there's more raw ingredients for future rings if they are broken up. Thanks for joining us, Jeff. So there we have it. Perhaps rings are the gravestones of previous satellites. We've just received word that the receiving station in Australia is reporting that the weather there is clear and quiet. So the weather on Earth is bodes well for fantastic images of the weather on Neptune, 2.7 billion miles away from Earth. Our next update will be coming to you in a little less than an hour at about 11 o'clock. The theme there will be Triton, and we'll have Larry Soderblom and Torrance Johnson to talk about an exploration of the new world, Triton. For Voyager Update, I'm Rich Terrell. See you in a little while.